We're just going to be doing some example problems. Okay, and I'm going to get you to help me, but this is all just do examples. So let's take a look at this first one. The graphs of f and g are shown on the interval from 0 to 5. Let k be the function defined by k of x is equal to 4 minus f of x times g of x. Consider x equals 2 and x equals 4. Determine whether k is continuous at either of these values. Justify your answers using correct limit notation. Wow, that's a lot to do for just a part A, but okay. So I'm going to divide this in half because I need to talk about both what happens at 2 and what happens at 4. All right, so let's find what is k of 2. So that's going to be equal to 4 minus f at 2 times g at 2. So that's going to be 4 minus f at 2 is 4 times g at 2, which is 4. So that's 0. All right, so now we need to find the limit as x approaches 2. And we're already suspicious of this, but, well, because over here with the g, where we approach from the left and we approach from the right are different. So let's look at the left and the right. So we'll look at what's the limit as x approaches 2 from the left of 4 minus f of x times g of x. So that's going to be 4 minus. As x approaches 2 from the left, what does f of x approach? 4. And as x approaches 2 from the left, what does g of x approach? -1. But we're okay with that because that's still 0. Looking good so far. The limit as x approaches 2 from the right of 4 minus f of x times g of x is going to be 4 minus, well, hey, when we approach from the right, what does f of x approach? 4. So we're feeling pretty good about this, and g of x approaches what? 4. And that's 0. So that means that the limit as x approaches 2 of k of x is also equal to 0. Therefore, k is continuous at x is equal to 2. Everybody good with that? All right, let's look at what happens at 4. K of 4 is going to be 4 minus f of 4 times g of 4. So that'll be 4 minus, what is f at 4? 3. And what's g at 4? 1. So that's 1. So k of 4 exists. That's the first part. If the function doesn't exist at the point, how can it be continuous at that point? That wouldn't make any sense. So now we need to look at the limit. So the limit as x goes to 4 from the left of k of x. I'll just call it k of x the first time, and then I'll go ahead and start working on it. So that's going to be the quantity 4 minus, as we approach 4 from the left, f approaches 1. Oh, sorry, approaches 3. And as g approaches 4 from the left, it also approaches 1. So we're like, okay, cool. This is going to be 1. It's looking good. Then we do the limit as x approaches 4 from the right of k of x. It's going to be 4 minus. As we approach 4 from the right, f approaches 3. So like, this is going to be exactly the, oh, wait a minute. Not so much, is it? Because as we approach 4 from the right, g approaches 4. So that means that the limit as x approaches 4 of k of x does not exist. Therefore, k is not continuous at x equals 4. That's the rainstorm we had earlier this week where it just poured was like this, or was that last week?
Yeah, at the beginning.
We've had a lot of rain recently.
I love it.
Yeah, I'm a fan.
I like the rain.
All right, so let's go down to part B. Values of f of x, that selected values of x are given in the table below. Based on the values in the table, what is a reasonable estimate for the limit as x approaches 1 of f of x? What type of discontinuity does f have at x equals 1? Give a reason for your answer. So, do we care that this is undefined at 1? No, we don't care what happens at 1. So I'd say, okay, it says give a reasonable answer, which means there's probably more than one. What do you think?
2.7, 7, 8, 5, 8, 6.
Yeah, either of those would be reasonable, wouldn't it? Right? Because it's in between what we know so far. What type of discontinuity does f have at x equals 1? The function doesn't exist here, but the limit does. What does that have to look like? It has to be a simple hole in the graph. What's the correct word for that? There we go. It's a removable discontinuity. How do I know it's a removable discontinuity? Because the limit as x approaches 1 of f of x exists, but f of 1 does not exist. That's the definition of a removable discontinuity, which is maybe why you don't talk about it, before you get to higher level math classes, because you haven't talked about limits. All right, let's move on to the next one. It is known that, wow, that was nice of them. to point out that the limit as x goes to 0 of sine of 2x over 2x is equal to 1. We should all know that. Okay, but they're prompting you a little bit. What is the limit as x goes to 0 of tangent of 2x over 6x secant of 3x? What just happened? Well, okay, so let's deal with this by making everything into sines and cosines as much as possible and then seeing what we can do with it. So this will be the limit as x goes to 0 of sine of 2x over cosine of 2x over 6x times secant is 1 over cosine, right? And this is, sorry, 3. I'd really like to get rid of the complex fraction. Again, I think it's easier to do most of these problems if you get rid of it. Occasionally it makes it worse, but that's one of those things you just kind of learn by experience. There's no other good way to do it. So I'm going to multiply this by both cosine of 2x and by cosine of 3x. So that'll be the limit as x goes to 0 of sine 2x times cosine of 3x over 6x times cosine of 2x. Notice we haven't quite gotten to where we're using this. It prompted us, like, oh, okay, well, I've got sine of 2x over 6x, huh? Maybe I could rewrite that somehow. Maybe I could go, okay, this is 3 times 2x. Now, what does cosine of 3x over cosine of 2x go to as x goes to 0? As x goes to 0, what does cosine go towards? 1. Cosine of 0 is 1. That needs to be another one of those ones that's easily at your fingertips. So that goes to 1. This goes to 1. So this whole expression goes to 1. What does sine of 2x over 2x go to as x goes to 0? 1. Told us this right here. Sine of 2x over 2x goes to 1. I still have a 3 in the denominator. So this is 1/3.
If there's like a number in front of the x, it still goes to 1 anyway?
Yeah, so you could actually factor a 1/3 out of this whole thing and put it in front of the limit because it's not affected by the fact that x is going to 0. Okay? All right,
I have a question.
I have an answer.
If you, so like, at the very start, we did sine 2x over cosine 2x over sine x times whatever, whatever cosine of 2x. Could you just put the 6x in the numerator there, and then just multiply?
Wait a minute, how can you put the 6x in the numerator?
Not the numerator of the one, like 6x over cosine 2x in the denominator. And then just,
Oh.
and then multiply by the reciprocal in the numerator, and then just cancel out the.
Yeah, you end up with the same thing. Yeah, absolutely. You could do that.
Instead of multiplying by cosine 2x.
Yep, it works out the same way. Good thought. All right, let's take a look at this one. For the function defined above, what is the limit as x approaches 2 of f of x? Anytime you've got an absolute value involved with that, we're probably going to want to look at the limit from the left and the limit from the right. So the limit as x approaches 2, I'm going to do it from the right first, of x minus 2 quantity squared sine of x over x minus 2. So as x approaches 2 from the right, sorry, I left off the absolute value. Notice that x minus 2 is always a positive value, right? So does the absolute value change it?
For some values. Yeah.
For values that are close to 2 but slightly bigger than 2? No. So for this limit, right, we can say that this is equal to the limit as x approaches 2 from the right of x minus 2 quantity squared sine of x over x minus 2. Well, x minus 2 squared over x minus 2, I can cancel those because other than at x equals 2, those are equal to each other. So now as x goes to 2, that goes to 0 times sine of 2. I have no idea what sine of 2 is, but I'm multiplying it times 0, so I don't care. This goes to 0. And then if I take the limit as x approaches 2 from the left of, to save myself time, I'm going to write just f of x. Now, if you have values that are less than 2 and you're doing x minus 2, you're going to get what kind of results? We'll get negative, but we want to change them to positive. So how can we change them to positive? Just in general, if you want a negative number to suddenly become a positive number, what do you want to do? Multiply by negative 1. So I'm going to say that this is equal to the limit as x approaches 2 from the left of x minus 2 squared times sine of x over negative 1 times x minus 2. It doesn't end up mattering, does it? But to show your work, it matters a great deal. This also ends up being 0. So the limit as x approaches 2 of f of x is equal to 0. So what type of discontinuity is this? Pardon? Yeah, it's removable. This is different than the other one. On the other one, f at that point didn't exist, right? The one on the first page. Here, f at 2 exists. It's just not what I want it to be. I would need to move it to make this continuous. That's also another way to think about why it's called removable. If I could move this, I could remove the discontinuity. All right? It's a removable discontinuity because the limit as x approaches 2 of f of x exists, but is not equal to f at 2. We are not going to get to all these. Wow, that's a lot of examples. Let's see which one I want to do. Let's do this one first, and if we have time, I'll do one more. So if f of x is equal to this piecewise function, where c is a constant, for what value of c is f continuous for all x? So in order to be continuous, the function has to exist at a point, and the limit has to exist at the point, and the two have to be equal to one another. So the function at -1, f of -1 is 4 minus cosine of -1. I have no idea what that is, and it doesn't matter. It's a real number, so the function exists there. Now what I want to have happen is the limit has to exist. So I'm going to look at what is the limit as x goes to -1 of, we know that this branch is going to match, right? It's this branch that may not. So of c plus 5 natural log of x plus c. And we want this to be equal to 4 minus cosine of -1. This is a calculator problem. If you've got cosine and natural log, there's no way you can do this without a calculator. I wish that the solver on your calculator was better than it is. The solver on the TID4 is suboptimal. It inhales sharply. But it's the best most of us have, so wake up. Y equals, clear you out, clear you out. I'm going to put this expression with x is -1 in y1. So I'm going to say, I can't say c because, well, my calculator doesn't like it. 5 natural log of, putting in -1 for x, plus c, which I'm having to call x. And I want that to be equal to 4 minus cosine of -1. So I've got these two functions, and I just want to see where do they intersect. What value of x makes both of those equal? So I have no idea where I was, so I always do a zoom standard to start. And then if I can't see anything at all, I usually do a zoom fit. So I just want to see where these two intersect. Calculate the intersection. First curve, second curve. Oh, it's always fun to guess on these. I'm going to guess 1, 2, 3. I'm going to guess 2.85. Boy, it didn't like that, did it? Why is it not doing anything? Find the intersection, first curve. I think I broke it. Is y'all's working okay? So what'd you get for C? Or for X?
2.268.
2 point what?
268.
268? I said 2.85? That's not a very good guess.
Is it the Y number or the X?
It's the X value. All right. Y'all have a terrific weekend. I'm going to hand you your worksheet, or Mr. Mediz is going to hand you your worksheet
For the last